The empirical rule. Our objective: use the empirical rule to describe data that are bell-shaped. Okay, we've seen data that are bell-shaped, that are skewed left, and that are skewed right. We're focusing on data that are bell-shaped here. The empirical rule only applies to data that are bell-shaped. What do we know that's going to help us in this lecture? We know what standard deviation is. How far, on average, each observation is from the mean. That's the standard deviation. Okay. When the data have a distribution that is bell-shaped, that is also called a normal distribution, because normal things like our heights, our weights, our SAT scores, etc., are bell-shaped. Okay? When the data have a distribution that is bell-shaped, the empirical rule can be used to determine the percentage of data that lie within k standard deviations of the mean. All right, so we can interpret this, and we'll do a fair amount of this coming up in future studies, future objectives in the course. Okay, what is the empirical rule? The empirical rule is also known by 68, 95, 99.7. 68%, 95%, 99.7%. And this really is where so much of things in real life fall, because so much of things in real life are normal. They have a bell-shaped distribution, and we can interpret information from that bell shape. If a distribution is roughly bell-shaped, if it's normal, then approximately 68% of the data lie within one standard deviation of the mean. Okay, let's go down to here and take a look. I can probably get both of these in there. I think I can. So here's the mean. Okay, there's the mean. Mean plus one standard deviation, mean minus one standard deviation. 68% of the data lies within that zone, if you will. Okay? In other words, most of us and most things are normal. Most of us and most things lie close to the mean. Okay? Example, shoe sizes. If the average shoe size for men is a 10, most of us have shoe sizes that are maybe from 8 to 12. Size 8 to size 12. Yes, we've got people, principally basketball players, who get really, really large shoe sizes. Yes, we've got people who get really, really small shoe sizes, but most of us are lying close to the mean. Okay? So that's the 68%. The 95% in the empirical rule. Approximately 95% of the data lie within two standard deviations of the mean. Okay, mean minus two standard deviations, or mean plus two standard deviations. So, cover my fingers from here to here, the part that's showing 95% of normal data lies in there. Okay, go back to my shoe size example. Let's pretend that if we have a size 10 for men and the standard deviation is 2, well, 10 minus 2 gets us to a size 6. 10 plus 2 is a size 14. 95% of men are going to have a shoe size of between 6 and 14. The vast majority of us. And that kind of makes sense as we think about it. Yes, there are people who have sizes above size 14. Yes, there are men with sizes below 6. But there aren't many. Okay, there aren't many. 95% are between here and here. And this is the big one that statisticians use a lot. 95% fall within this from here to here. The last piece to the empirical rule, come down here and show it to you, is the 99.7. And it says to us that approximately 99.7, so now we're talking almost precisely 100% of the data lie within three standard deviations of the mean, between the mean minus 3 times the standard deviation and mean plus 3 standard deviations. Go back to here. So here is the mean minus 3. Here's the mean plus 3. So if I put my figures here and here, and what it's showing is 99.7% of the data is in this zone. Yes, a very, very small percentage of the data, 0.15%, is larger than the mean plus 3 standard deviations, and a very, very small percentage of the data, same, 0.15 cents, is smaller than the mean minus 3 standard deviations, but really almost everybody is here to here, with just rare exceptions. This goes on mathematically forever. Rare exceptions to get beyond the mean plus 3 times standard deviation, or beyond going the opposite direction, mean minus 3 standard deviations. So this is it right here. This is the normal distribution. It's the bell shape, and it is the empirical rule that we're going to play with when we get into another unit and talk about normal distributions. This has a lot of value and is probably the most often used statistical analysis or statistical conversation when it comes to what you'll see in real life, because so much of what is out there is normally distributed. It's bell-shaped distributed. Okay. Whoops, I gotta get my other page out. Just a second. What did I do with my other page? There it is. Okay, let's see here. Example 1. We're gonna create a normal distribution. The data in StatCrunch represent the length in seconds of eruption for a random sample of eruptions at the Old Faithful geyser. So we're going to go 3, 2, 2, 6 for the number of seconds for a random sample of eruptions. What is the mean and the standard deviation, both rounded to the nearest whole number? Okay, I'm going to go into here and calculate those. I don't want to do them by hand. So we're in chapter 3. We're talking about 226, which is here. We'll click there. So here's our data, length of eruptions. And it looks like somebody did this 44 times. They timed 44 eruptions in seconds. They got all this raw data. That's a sample. And want to find the mean and the standard deviation, both to the whole number. So we'll go to Stat, Summary Stats, and we know their data's in a column. We'll select our column, and we know that it's one of our defaults. Here's the mean, here's the standard deviation. It's a sample, so we'll use standard deviation, and we're going to compute it. And our mean to the nearest whole number is 104 seconds, and our standard deviation to the nearest whole number is 6 seconds. Okay, so let's go back to here. Let me make use of this. I'll give this up a second. Okay, let's go back to here, and let's make a note of that. Okay, so the mean of the sample, X bar, is 104 seconds. So again, it means if all the eruptions were the same length of time, they would all be 104 seconds. The standard deviation for our sample is 6 seconds. Okay, so the average distance, the length of time is from the mean is 6. Okay, use StatCrunch to create a frequency histogram. Is the graph roughly bell-shaped and thus appropriate to use the empirical rule? Remember, the empirical rule requires a bell-shaped distribution, or a roughly bell-shaped. It cannot be skewed left or right. We need to check this. Is this data roughly bell-shaped? Let's go back to here. I left it up, kind of left it up. I'm going to go, I guess I got to close this because I got to go back to, I'll go back and close it. 3/2/26, I think. Yep, there's my data. Graph histogram. Excuse me, my column is length of eruption. I can do a frequency histogram. That's already selected. We don't need to we can put values above the bars if you want to. Let's go ahead and compute it. There it is. Is this roughly bell-shaped? Yes, it is. As far as we're concerned, yes, this is roughly bell-shaped. You know, these two kind of get countered by that one. We have it's roughly, I don't really see a major skew here. It's not majorly skewing off to the right or the left with a long tail. So we can say, yes, this is roughly bell-shaped. Okay, now that's obviously a judgment call to some degree, but we're going to say that is roughly bell-shaped. So back to here, and the answer is yes. So we can use the empirical rule. Okay. Here's our bell-shaped curve. We're gonna say it's normal. Okay. This is in the middle is the mean. So this is the mean in the middle, and then we go off to the right and left by adding and subtracting standard deviations. Our mean is up here. Our mean is 104. So we'll go down here and we'll put 104 here as our mean. A bell-shaped distribution is symmetrical with respect to the mean. So the mean is at the pinnacle of our bell. Okay, standard deviations. Our standard deviation is 6. So if we say, okay, I'm going to add, this way I'm going to add 1 standard deviation, then this is going to be 110. I added 6. And then I'm going to add another standard deviation. I'm going to add 6 to get 116. And this is the mean plus. So this is plus 2 standard deviations. I'll add again. I'll kind of go like that for the plus 2. I'll do another plus 6. I get to 122. And that is plus 3 standard deviations. Let's go the other way. If I subtract 1 standard deviation, so I'll subtract 1 standard deviation, subtract 6 to 98. Go back a second standard deviation, subtract 6 to 92. Go back a third standard deviation, I get to 86 when I subtract 6 again. Okay, so here is my distribution as a normal distribution. And I can now use the empirical rule. And what do I know? Well, between 1 standard deviation above and 1 standard deviation below, this is 68% of my data. Okay, so I'll just make a note of that. This is 68%. Okay, so 68% of the eruptions that took place were between 98 seconds and 110 seconds. Okay, now this is symmetrical, so this one is 34%, this half, and this half is also 34%. How about the 2 standard deviations? Well, that's 95%. 95% is between 2 standard deviations. Okay, so 95% of the eruptions from Old Faithful were between 92 seconds and 116 seconds. Okay, so that's almost all of them, 98%, right? 95%. 95% are right here. Okay, and now we know there are 3 standard deviations. The empirical rule is 99.7. So if I can draw this reasonably closely. Okay, so 99.7%. That's pretty good. Kinda. Okay. 99.7% of our eruption times are between 86 seconds and 122 seconds. And again, that's almost everything. This goes on forever, so you're never going to get 100% precisely, but 99.7% obviously gets us pretty close. And again, we can cut this in half. If this is 95%, then this half is half of 95, or 47.5%. This half is half of 95, or 47.5%. Okay. According to the empirical rule, and I'm going to pull this out to also take a look at the percentages. What percentage of eruptions last longer than 104 seconds? So number one here. Here's the 104 seconds. I want longer. I want this half. The 104 is the median. It cuts it in half, 50-50. So 50% lasts longer. So greater than 104 would be 50%. In a normal distribution, the mean equals the median. Let me come down a little bit so I can show as I'm pointing to it. The mean and the median are the same. It's symmetrical, so it's 50%, 50%. And so greater than 104 seconds, half of the data. Okay, how about number two? Between 92 and 116. So from 92 to 116, well, that goes from here to here. That's from here to here. Well, that goes right with our rule. That's 95%. What percentage of the eruptions? 95% of the eruptions last between those two. Less than 98. A little trickier to figure out. Okay? We know that this half is 50%. Okay, so that's 50%, but we want to be less than here. We want to be over here in this area here. Well, we can do it mathematically and say this is 50. We know that this part is 34 because this is half of the 1. So we could say 50 minus 34. And we would come up with 16%, which is the answer. We can also look at this table, which would give it to us. Here's the 34. So I took this half, 50%, and I took this 34 out to get this. We could also add up this plus this plus this, and we would get 16. Okay? And number 4. Whoops, you got to be able to see on my paper. Sorry about that. Longer than 116, greater than 116. Well, that is this small part over here, right? Just this area over here is the eruption times that are greater than 116. How much is that? Well, let's use this chart. Okay, so we'll use this chart. Well, this piece is 2.35. This little piece beyond the 3 standard deviations is 0.15. If we add up 2.35 and 0.15, we get 2.5. So we'll just make use of that chart to say that 2.5% of the eruptions last longer than 116 seconds. So there you have it. I don't think there's anything else with this. Nope, there you have it. Some work with normal distributions, some beginning work with normal distributions, and the empirical rule. We're going to come back to this a fair amount. So work on remembering it and making sure you understand it.